Hi folks, we're going to take a look at number 18 from page 570 on the Unit 4 assignment. So let's take a look at the question here. So it says, shadow cast by a man standing 1 meter from a lamppost is 1.2 meters long, gives us the height of the man, and tells us that he's walking away from the lamppost at a speed of 100 meters per minute. Okay, at what rate is the shadow lengthening after 5 seconds? Okay, so the fact that they're giving us the rate of one variable changing, in this case here, distance away from the lamppost, and they're asking us to determine another rate. Okay, that's what makes this a related rates question. So what we have to do now is find a way to relate those two variables that are changing. Okay, so anytime there's sort of a geometry to the question, often a diagram is going to be the key. Good diagram is going to be the key to solving the problem. Okay, so here we've got a lamppost. Okay, and we've got a man, okay, 1.8 meters tall, okay, and a shadow is cast. Okay, so let's see what they give us. They tell us the rate at which he's walking away from the lamppost. Okay, so we're going to be interested in this distance, which is increasing over time. Okay, and as the man walks away, okay, makes sense that the shadow is going to get longer and longer and longer. So what we want is we want to determine how is this length changing over time, and it should be increasing. Okay, so we need to find a way to relate these two quantities. Okay, so let's take a look at the picture. Okay, you take a look at it, you see a bunch of right angle triangles. You might think Pythagoras, but there's no information given about the hypotenuses of these triangles. So while we do have right angle triangles, it doesn't look like that's going to be useful to us. Okay, hopefully you're going to notice that I've got something else going on. I've got two similar triangles here. Okay, because I've got this smaller triangle and then the larger triangle created with the lamppost. Okay, are similar triangles because they both have a 90-degree angle and they both share this angle, so the third angle must also be the same. Okay, so this is what I'm going to try to use. Okay, because what I can do is I can compare this side of the triangle, the smaller triangle, to this full side of the larger triangle. Okay, so x and, well, this would just be d plus x. Okay, so again, no information about the hypotenuse. So I've got this 1.8. The question is can I figure out the height of the lamppost? Okay, and this is where I'm going to use the specific information that they give me, and I'll actually redraw another picture. Okay, it says when the man is 1 meter away, okay, man is 1.8 meters tall, the shadow is 1.2 meters long. Okay, so this length is 2.2. Okay, so I can compare these two lengths, 1.2 and 2.2, and now I'm going to compare the height of the man, which is this side of the triangle, to the height of the lamppost. Okay, and that's the only variable I don't know. Okay, so I'm going to go h over 1.8 is equal to, well, since I started with the larger triangle, got to start with the larger triangle there, is equal to 2.2 over 1.2. Okay, so let's just calculate that here. So what do we have? So we have h is equal to 2.2 times 1.8 divided by 1.2. Okay, 3.3. Okay, and since the lamppost doesn't change even as these other quantities are changing, the height of the lamppost is always the same. Okay, so now here I can put 3.3. Okay, and now I can set up an equation to relate my two variables. Okay, so what I have here is, let's start with this smaller. Okay, it doesn't matter whether you start with the smaller or the larger, but here I've got this side of the triangle. Smaller triangle corresponds to that side of the larger triangle. So I have x divided by, and as we said, this whole length is d plus x. is equal to the ratio of those two corresponding sides is equal to 1.8 over 3.3. And I actually have quite a simple relationship that connects these two variables. So let's do a bit of rearranging here and before I take a derivative. So here I've got 3.3x equals 1.8d plus 1.8x. Okay, bring that to the other side. So we've got 3.3. I know I shouldn't be doing this, but a little late tonight. Minus, what is it? 1.8. There you go, 1.5. Should have been able to do that in my head. Equals 1.8d. Okay, so this is my relationship between the length of the shadow compared to the distance from the lamppost that's changing. So what I'm going to do now is take the derivative with respect to t of both sides. Okay, so 1.5 is just a constant, so I got 1.5 dx dt. Okay, and then 1.8 dd dt. Okay, and I know that his distance from the lamppost is increasing at, it was 120 meters per minute, so dx dt is just going to be equal to 1.8 over 1.5 times 120, and so that's equal to, let's see what that's equal to. So 1.8 divided by 1.5 times 120 is 144. Okay, so that's going to be 144 meters per minute. And there you go. That's the solution to the problem. Now, one thing that's interesting is that they actually gave us a little more information than needed, because they're saying at what rate is the shadow lengthening after 5 seconds. But we see here that we didn't even need that information to solve for the problem. Okay? Now that makes sense because the relationship between x and d is a linear relationship. So we would expect that that rate of change would be constant, that it wouldn't depend on the amount of time that has elapsed. Okay, so in this case here, they maybe threw a little wrench at us by, they tried to fish us in by thinking that we'd have to bring in that 5 seconds. Okay, so just a recap here. Again, it's all about having a good diagram, okay, and not just assuming that because it's a right angle triangle, it must be working with Pythagoras, but to see that you have two similar